So for the first module of Chapter 4, we're going to look at how to compute the moment of a force using what's known as a scalar formulation. So when you hear that we're going to do it using a scalar formulation, what you probably assume is that whatever the moment of a force is a vector quantity, and that's correct. And hopefully by the end of this learning module, if you want to go back and kind of write this down and make sure that you understand this, you will understand the physical meaning of what a moment of a force is. As I mentioned, it's a vector whose magnitude describes how likely or the tendency of a force to actually induce rotation in the body, and the direction of that vector actually defines the axis of rotation about which that rotation would occur if the force were actually allowed to induce rotation. Of course, we're talking about statics, so ideally nothing is going to be moving. What is going to be happening is when we have a force that would induce rotation, the actual structure that's counterbalancing those applied loads is going to have to kind of cancel that out, for lack of a better term, much in the same fashion as we did with the actual translational forces that we talked about in chapters 2 and 3. And just in case anyone's confused what I'm talking about, if I have a body like my cup here that I often use, it can move or kind of shift from one point to another. That type of motion is called translation. In addition to moving or translating from one point to the other, it can also undergo a bit of rotation. Now, rotation, the easiest way to think about it is to not kind of just ignore translation and think about it as something were to rotate, and let me hope that there is no actual fluid in this cup. I think I lucked out. And when you have that rotation, notice that naturally you always define rotation about an axis. So as you were watching that occur on your screen and maybe hoping that fluid was in the cup, that way I got stuff all over me, you noticed that that rotation looked like it was occurring about an axis that was coming directly at you. So moments of a force are naturally vector quantities, but we're going to talk about here how to compute them using a scalar formulation. So the first bullet is what I just said. When you have forces acting on a body, they're naturally going to tend to induce translation and rotation. And what the moment of a force actually describes is the tendency of a force to induce rotation about a particular point. So that's really, really important here. Whenever we compute moments of a force, they're going to be about some point of reference. You've probably heard this used in kind of your everyday day-to-day life as torque. And maybe when you walked out a door today and you knew where the hinges were on that door and what you wanted to do in order to open it was to either push or pull in order to induce rotation about those hinges, you had two choices to make. You picked how hard to actually push or pull. That's kind of like the magnitude of your force. In addition, you chose where actually to put your hands. So you kind of knew, ideally, hopefully, if you open the door correctly, you position that push or pull as far away from the hinges as you can, because you know that the actual tendency of a force to induce rotation is not only related to the magnitude of the force or how hard you push or pull, but also how far it is positioned away from the actual point about which you're trying to induce rotation. That's not a great example because there you're trying to induce rotation about an axis. But think about, for example, like if you've ever tried to loosen a fastener, maybe a bolt that just was really, really hard to get loose. Maybe it actually corroded a little bit due to water, and you got a wrench on there and you're trying to loosen it and it just doesn't move. Well, there's two things you can do. One is to actually go grab some kind of lubricant like WD-40, but maybe in addition, you actually go and grab a longer wrench, because you know if you're to apply the same force with a wrench that's twice as long, it's actually going to induce twice the amount of torque on that bolt and actually induce rotation about an axis, which is perpendicular to the head of the bolt, which is what you're trying to do to get it loosened. So hopefully if you got anything from the slide, you know that when you're talking about moments of a force, you're talking about the tendency of a force to induce rotation. It's also called torque, and it's a vector quantity. Its magnitude describes like how much of a tendency you have to induce rotation, and its direction actually describes the axis of rotation. So when you think about forces that are actually acting in a plane, say I like had this piece of paper here on my dot cam, and I try to apply a force that's purely in the plane, meaning I don't push down into it. I just push ever so slightly kind of in the direction of the paper. Notice that the forces that are generally in the plane are going to tend to induce rotation about an axis which is perpendicular to that plane. So if we use our traditional kind of coordinate systems, and we refer to this as positive x and this is positive y, we talked about a little bit in the actual second chapter of the text that the coordinate systems that we talk about in this text follow a right-hand rule. So if I curl positive x into positive y, and we'll talk about what that all means a little bit later on in this chapter, that's going to create a z-axis that's actually going in this direction. However, what happens with coplanar force systems is rather than actually dealing with vectors to describe the axis of rotation, you can use simply a scalar sign, plus or minus, to indicate the actual direction of the moments. And the reason is, yeah, technically they're all about the z-axis. However, since they're all about the z-axis, why even waste your time writing that? Why not just say whether it's a counterclockwise rotation about the z-axis or a clockwise rotation about the z-axis? So look at what happens is this is positive x and this is positive y. And say I am trying to understand how a force applied here that is actually going in the vertical direction would induce rotation about the z-axis. So say I actually pin my paper here and I actually push up, exerting a force in the positive y direction. If you notice in that case, it looks like it's rotating about the positive z-axis. And notice that that rotation, if you were to actually describe the direction that the page is moving, is actually counterclockwise. So rotation about the positive z-axis is actually rotation that in the plane appears to be counterclockwise. Minus is actually rotation that appears to be clockwise. So we're going to use plus or minus in this case, or counterclockwise or clockwise, to actually define the direction of these moments. But the key thing I want you to realize is they're still vector quantities. That's still a rotation about the z-axis, but since in 2D, all rotations will be about the z-axis, we'll just use this simplified description. So this is how you actually compute the magnitude, and we'll look at how you compute the direction of the moment using a scalar formulation. So this is direction, and this is all using the scalar formulation, because what we're going to see is if we can actually define a cross product, we don't have to do any of this stuff. So how do I determine the magnitude? Well, what we're going to find is that the magnitude of a moment is nothing more than a quantity known as the perpendicular distance. And this relates back to that kind of lever arm idea that we were talking about earlier when we were talking about the length of a wrench, times the actual magnitude of the force. And oftentimes what we'll see is if we decompose the force into components, the computation will be easier. And that's what the book is trying to show you here. Imagine you had a body, and we're actually not seeing it here, but we're just actually given some geometrical distances between some point of reference O and a point of application of the force over here. Say you wanted to compute the moment of this force about this particular point. Well, look how much easier it is if you decompose the force into horizontal and vertical components. And the reason that it's easier is twofold. First and foremost, if you do this, it's very easy to determine the sense of the rotation induced by the y component and the x component, and I'll show you that in a minute. But in addition, it's very easy to get the perpendicular distance in terms of quantities that you're given. So I'm actually going to draw this out. I have my origin, I have my vertical displacement B, I have my horizontal displacement A, and I'm actually applying a force that looks like it's somewhere up there in the first quadrant. Who knows? Maybe it's just some direction theta. So I'm going to go to my dot cam now. Now imagine that I did a decomposition of this force into a vertical component and into a horizontal component. So call that Fx and call this Fy. Notice that if I pin the actual body at O and I actually pull the paper in the direction of each of these forces, clearly if I pin here and I push up, that's going to induce a counterclockwise rotation. So in terms of if I were to actually try to determine the scalar formulation of this moment, I can get the sign of it pretty easy. In the same fashion, if I pin it here and pull in this direction in the positive x, notice that that is inducing a clockwise rotation, which remember is rotation about the negative z-axis, so we'll just denote it by a negative. So one of the advantages of kind of decomposing this force into components is you can easily see the sense of rotation that they induce. Another advantage is if I extend out the actual lines of action of each of these forces, I can easily compute the perpendicular distance, because the way that I compute the perpendicular distance, and imagine this was actually a straight line, is I go from the point of reference, in this case O, and I ask myself, there's a ton of lines I can draw from O to the actual line of action of that force. But there's only one that I can draw that actually creates a perpendicular geometry. And this is actually the perpendicular distance for the y component. And if you notice, we were given that that is A. In a similar fashion, if I extend out the horizontal line of action of this force, there's a ton of lines that I could draw from the origin to that horizontal line. However, the only one that actually creates a perpendicular intersection is the one that goes directly up. And clearly this B is nothing more than the d-perpendicular distance for Fx. So if I were to want to compute like what the moment of the force Fx was, and this is for the force Fx, it would be nothing more than, well, the first thing I have to do is add in my sign corresponding to the sense of the rotation. Then I multiply by my perpendicular distance, which is B. And then I just multiply by the magnitude of the force, which is Fx. Or maybe I could write that as minus B F cos theta. In a similar fashion, if I wanted to write what the moment about point O was for the y component of the force, notice that I will add my sign, which is positive because it's tending to induce a counterclockwise rotation. We said that the perpendicular distance was actually a, and I'll multiply by the magnitude of the force, which is just Fy. So it would just be F times sine of theta. So this approach that we're actually showing here is how you actually do the scalar formulation for moments. And notice that obviously you're only going to be able to do this in 2 dimensions, right? It'll become incredibly complicated to do in 3 dimensions. So let's actually look at some example problems here. In this first example, for cases A through C, we're trying to determine the moment of the force about point O. Well, I'm not actually going to draw these out. Let's actually just kind of do them by pointing with our mouse and describing them. If you notice in this case, this 100 Newton force, it has a line of action which is purely vertical. If you actually hold, if you were to draw this, and pin your hand at point O and actually pull that rod down, notice that the rotation that you're going to get is in the clockwise direction. So when you actually determine the sign or the direction of this moment, you're going to need to add in a negative. In addition, the perpendicular distance is actually the length of this rod, because if you draw a line from point O to the line of action of that force, the one that is perpendicular will be 2 meters long. So this moment, if you were to actually write what it is, you would say that the moment of that 100 Newton force about point O, which you traditionally would just denote as, and I'll show you this just written, you denote it as MO. This is the moment of the 200 force about point O. I'm going to put a negative in there. Since we did from the pinning, we saw that it would induce a clockwise rotation. The perpendicular distance is 2 meters, and the magnitude of the actual force was 100 newtons. So if you actually compute out that quantity, what you'll see is this is minus 200 Newton meters. So that's how you actually do a scalar formulation for the moment of a force about a point. What about this one here? Well, imagine you were to pin that actual assembly at point O and actually push it in that direction. Hopefully everyone sees that that also induces a clockwise rotation. And if you don't, let me just sketch it real quick. If you had something like this, which is the geometry that we have, if you pin it at point O and you push it in, notice you're going to get a clockwise rotation. So this force, if you were to actually try to determine what its moment is using a scalar formulation, the first thing that you would do, so if this is O, this is F, the moment of that force about point O, I'm going to add in a negative, because if I pin at O and push in that direction, it's a clockwise direction, a clockwise rotation that would be induced. The perpendicular distance in this case, notice if you extend out that line of action, is just going to be this quantity right here. So that's just the length of that little segment. So that is going to be a length of 0.75. So don't just think, oh, it's 2 meters away. The perpendicular distance must be 2 meters. You actually have to see from the geometry what that is. And then you're going to multiply by 50 newtons. And that's going to be some quantity in negative Newton meters, whatever that turns out to be, 50 times 0.75. Notice that in the last one, hopefully everyone sees by now, this 40-pound force is actually also going to induce a clockwise rotation. So that's going to get a negative to it. The thing that makes this problem a little bit tricky is you're not given the geometry corresponding to the perpendicular distance directly. However, you can calculate it. Notice that the perpendicular distance is just going to go from O directly to the horizontal line of action. And that will be 4 feet. That's this portion of the rod. And in addition, you can use the 2 feet length of the rod with that geometry that you're given in order to compute that additional distance, which is 2 cos 30. So the perpendicular distance in this case from point O is 4 plus 2 cos 30. So hopefully that makes sense to everyone. So I'm actually going to record this second example here in a different video, because I think I'm getting a little bit long on this video, longer than I typically like to make them at the 14-minute mark. So I will see you in the next video with another example.